So last Halloween, I followed this tutorial on how to make a cardboard Boba Fett helmet, but I stopped short of the part with the little rangefinder thing, because for that, I had other plans. So this guy over here is sort of the central hub of this operation. It's just a microcontroller, so think of it just as a really tiny, crappy computer. And then the silver thing it's on top of is just a battery bank. So this guy is an infrared array, and basically it's kind of like a thermal camera, except in exchange for not being $100 or more, it only has a resolution of 8 by 8 pixels. So yep, 64 pixels total. We'll get to that. There's this screen, which is just a cheap, low-resolution OLED screen. And importantly, it can display nothing or blue. There's no in between. Then last but not least, the microcontroller is controlled by an actual computer, which is this Raspberry Pi. And it's not technically necessary, but it's convenient, and also there's other future stuff that's going to depend on it. First though, let's address the only having 64 pixels problem. I just need to, 1 second. All I need to do is get out my bag of tricks, which currently contains bilinear interpolation and Floyd Steinberg dithering. That's an awful lot of fancy pants technical jargon nonsense, but nothing here is actually that crazy. All right, so let's start with bilinear interpolation. But before we do that, we'll have to talk about normal linear interpolation. And the way linear interpolation works is very simple. It's just, we have like a sparse set. Maybe we know at this point the temperature is 0.2 or whatever, and maybe over here it's 0.8. I don't know, it doesn't actually matter. Well, we want to find it somewhere, along this line, somewhere in between here. And what we'll do is we'll just have two components. So we'll say, if it's all the way over here, we'll put this distance, the first one, we'll call it t. And then we'll say, okay, well, if we're all the way over here, in which case t is 0, then we want it to be 0.2. So we'll do like 0.2, 1 minus t. So that handles the 0.2 side of things. Then we can add the 0.8 side of things, which when will we always be 0.8? Well, when t equals 1. So we'll just do it like that. And that's all there is to it. It's just very basic math to, if I were to draw this as a graph and you were to have like 0.2, 0.8, we would literally just be drawing a line. Okay, but how do we do this in 2D? Because now we have, 4 points, right, that were in between. So these are like the corners of the sort of nearest pixel or whatever. These are the 4, known points that we're closest to. And the trick is to realize that if we're over here, right, we're somewhere along this line, then we can just do normal linear interpolation, right, because there's two things between here. It should be easy. So we can do that. We'll say maybe our target, desired point is over here. We'll do that with the x value of our point. So that will just line up there, and we'll find the linear interpolation value there. And then we'll do the same thing with the bottom one. Again, just normal linear interpolation using the x component. And now we have basically the same situation before. We have 2 points, this time in the y direction, that are exactly in between our points, so we can just linearly interpolate between those. So that will let us finally figure out the point. So first we linearly interpolate between these two using the x value within this square. Then same thing but with these, and that gives us those 2 new points, which we can use the y value within this square to interpolate. That's all there is to it. So that interpolation step gives us an image like this, right, which is higher resolution and somewhat smooth. But it still doesn't solve the problem of us only being able to display black and blue and nothing in between, right? So we need some way to, these are values between, 0 and 255. We need to force them to be either 0 or 255. And the way we do that is by generating this other pattern, and the specifics don't super matter, but you can see it's just repeated, and inside each of these cells, there's just a bunch of evenly spaced values. So in this case, we have 0, 1/4, 1/2, and 3/4 of the way to 255. And what we're going to do is for each pixel, we're going to mark down whether the pixel in our real image is greater than the pixel value in this pattern. And when we do that, we get a sort of crude approximation of the original thing. So this process is called dithering, The specific technique with the grid is called ordered dithering. In person. And I duck out of the frame. Hello. Oh my god, this is freaking awesome. This is the big problem with ordered dithering. You can see if I put my hand here. Alright, suddenly it becomes very clear to see those patches. It just doesn't look great, honestly. So what we want to do instead is to not have to rely on a weird gridded pattern. So we'll just take one pixel at a time, and this one, has some value. And we're just gonna do our best to just round it. So if it's, above like 127, it's 255, it's below, it's 0. So we'll just round it up, do as best we can. But you can see that in this case, we ended up overestimating. And we can quantify how badly we overestimated by subtracting them. And this is called the quantization error, right? We overestimated by a value of 80. So now, when we move on to the next pixel, which we'll just say is the same thing, we can account for our previous mistake by intentionally underestimating it. So we overestimated the first one, we can underestimate the second one, and the idea is that eventually this will balance out. And how do we do that? Well, we take our quantization error and we subtract it from the value. And so in this case, that'll actually flip it to be a 0. And we can sort of write down what we're doing in this very simple matrix where the star is like the current pixel we're looking at. And what we're doing is we're taking all of the quantization error and pushing it onto the next pixel. What would really be nice is if we didn't push it all onto, one pixel, we could spread it out over a couple of the pixels that are nearby it. And that's why this technique is called error diffusion, because what we want to do is diffuse the error across many nearby pixels. And so in this case, only the next pixel only gets 7/16 of the error, and the rest is spread out about other, diagonally adjacent or adjacent pixels. So we can run that on the Arduino, and I mean, obviously it's a little bit difficult to not be subjective, but it's much better. It's definitely much better. So that's Floyd-Steinberg dithering. All right, here's your face reveal. So in basically any this isn't my footage. I definitely don't play Genshin. But in basically any game, you have this mini map in the corner, and I think it would be super cool to have one of those in real life, except not with my actual location because I don't want to dox myself.
A few moments later.
So the actual, screen that you can see is controlled by the microcontroller. We'll do microcontroller unit, and then that's controlled by the Raspberry Pi. And the way this works is this sends data over a very, very, very slow serial connection and a very, very, very sketchy protocol that I made. But it does the job for just updating maps every so often. And then to get the map images, it talks to an API to go get maps in this style called toner, which is already black and white, so no dithering required. Then, once we can do that, it takes the images, does some conversion things, and then sends it off to the microcontroller. But the problem is, we need to know where we are. It doesn't have the Raspberry Pi doesn't have a GPS. So, on the same Wi-Fi network is a website on my phone, which is being, the Pi is acting as a web server, and it's serving this website, which lets me manually control the map. In theory, if I wanted to dox myself, I could have it just get my actual location directly.
A few moments later.
I mean, I think it's pretty cool, but yeah, we can just move around. We go down. Maybe we'll go left a bit. Oh yeah, obviously there's a ton of lag because it has to go use the slow phone connection to talk to the computer, then get the image, then transform it, and then send it over a very slow USB serial link. I don't know. I just think it's really cool. I just don't feel like I'm getting through to you about how awful and sketchy and terrible and glitchy the link between the microcontroller and the Raspberry Pi is. I guess there's only one way to show you.